Section 6, we will discuss graphing linear inequalities in two variables. A linear inequality in two variables is written in the form ax plus by is less than c, and in place of the less than symbol, we could use any inequality symbol, greater than or equal to, less than or equal to. We say that an ordered pair is a solution of the inequality if when we replace x and y with the coordinates, it results in a true statement. Whenever we want to graph a linear inequality, we go through a three-step process. First, we graph the boundary line found by replacing the inequality sign with an equal sign. If the original inequality sign is greater than or less than, we graph a dashed line. If the original sign is greater than or equal to, or less than or equal to, we graph a solid boundary line. Once the boundary line is graphed, we choose a point that is not on the boundary line as a test point. We use the coordinates of the test point and substitute those into the original inequality. If a true statement is obtained in step 2, then we shade the region that contained the test point. If a false statement is obtained, we shade the region that did not contain the test point. So let's try a few examples. First, we want to graph 7x plus y is greater than negative 14. To start, our first step is to rewrite this inequality as an equation. Now, anytime we want to graph an equation, we need to have at least 2 points, so we can make an xy table. And we'll choose a few values to plug in for x and y, x or y, as long as we only choose one coordinate at a time. So let's start by substituting x with negative 1. That gives 7 times negative 1 plus y equals negative 14. That becomes negative 7 plus y equals negative 14. We then add 7 to both sides of the equation. The opposite 7's cancel on the left side, and we're left with y equals negative 7. So our first point is negative 1, negative 7. For the second point, let's plug in 0 for the y coordinate. It gives us 7x plus 0 equals negative 14. And remember, anytime we add or subtract a 0, it doesn't change any number beside it, so we just cross it out. That gives us 7x equals negative 14. And after we divide both sides by 7, we're left with x equals negative 2. Let's go to the next slide so we can plot these points and then go through with step 2 and step 3. So we have the 2 points, negative 1, negative 7, and negative 2, 0. So we go to our graph and we plot these 2 points. We go to the left 1 and down 7. For the second point, we go to the left 2. We don't go up or down at all because the y coordinate is a 0. We go and we look at the original inequality sign, and it is greater than. It does not contain an equal to, so we will have a dashed line. And once we plot that dashed line, it separates our coordinate plane into 2 regions. We now need to pick a test point that is not on the boundary line. It doesn't matter which side the test point comes from. Typically, I like to choose the smallest value possible when plugging in a test point. So here, let's choose 0, 0. That's a point that's clearly not on the boundary line. When we substitute that into the original inequality, we have 7 times 0 plus 0 is greater than negative 14. That becomes 0 plus 0 is greater than negative 14, or just 0 is greater than negative 14. And we can see that this is a true statement. 0 is in fact greater than negative 14. So we will shade the side that contains the test point 0, 0. Let's try another example. 3x plus 5y is less than or equal to -2. So again, we go through the three-step process. Step 1, we change the inequality symbol to an equal sign. And anytime we are graphing the line for an equation, we need 2 points. So we go back to our xy table. We pick coordinates for x or y, just not both at the same time. This time I'm going to try the coordinates -4 and +6 for x. So starting with -4, we replace x with a -4. 3 times -4 is -12. So we have -12 plus 5y equals 2. Excuse me, -2. We then add 12 to both sides. That leaves us with 5y equals 10. Then we divide both sides by 5, and we have y equals 2. Let's try again with the x-coordinate of 6. So we have 3 times 6 plus 5y equals -2. It gives us 18 plus 5y equals -2. And we subtract 18 from each side. We're left with 5y equals -20. We divide both sides by 5. We're left with y equals -4. So let's go to the next slide. Rewrite these two ordered pairs we found. -4, 2, 6, -4. We'll start by plotting these 2 points and then deciding what type of boundary line we will have. So -4, 2, we go to the left 4, and then up 2. For 6, -4, we go to the right 6, and down 4. We go and we look at the original inequality symbol. Because our inequality contained the or equal to, this is less than or equal to, we will have a solid line that connects these 2 points. Once we have plotted the boundary line, we want to choose any test point that is not on the boundary line. So I might choose this value in green, which would be 1, 2. You may choose a different value, and as long as it's not on the boundary line, that's okay. So we take that ordered pair and plug it into the original inequality. That gives us 3 times 1 plus 5 times 2 is less than or equal to -2. As we continue to solve, we have 3 plus 10 is less than or equal to -2, or 13 is less than or equal to -2. A positive number will never be less than a negative number. It will never be equal to a negative number, so this is a false statement. Because our statement is false, we do not want to shade the side of the region. We don't want to shade the region that contains the test point. So instead, we will shade the other side. Every time one side will be true, one side will be false. We always want to shade the true side, or the side that is not false. In the next example, we will go through the same steps. So step 1, we change the inequality symbol to an equal sign. And we notice we only have one variable present in our equation. Whenever that's the case, we go ahead and isolate that variable. So we divide both sides by 3. We're left with x equals 5. And there are multiple ways to remember how to graph an equation with just one variable. It may be just as easy to write the xy table again. Because x equals 5, we have no choice for the x-coordinate. The x-coordinate must be 5 every single time. And because there was no y variable present in the equation, y can be anything. So I might choose 0 and 3. Let's plot these 2 points. So the first point, 5, 0, we go to the right 5. We don't go up or down because the y-coordinate is 0. For the second point, 5, 3, we go to the right 5 and then up 3 units, and we have 2 points. We look at the original inequality symbol, and because it is a less than symbol, this will be a dashed line. For step 2, we choose a test point, and it can be on either side of the inequality or either side of the line that we've just graphed. So let's choose the smallest number possible, which in this case would be 0, 0. Substituting into the original inequality, we have 3 times 0 is less than 15. 3 times 0 is 0. So we have the statement 0 is less than 15, and that is a true statement. So we will shade the region that contained the test point 0, 0. Example of an inequality with just one variable, y is less than 2. So we go through the same process. We start by changing the inequality to an equation. So we have y equals 2. Here we can also make an xy table. And remember, because we have one variable equals one number, the y-coordinate is fixed. So the y-coordinate must be 2 each time. Because there's no x variable in the equation, x can be anything. I might choose 0 and 5. So now we can plot these 2 points. 0, 2, we move 0 units in the left and right direction, 2 units upward. For the next point, we move 5 units right, again 2 units upward. We look at the original inequality symbol, and because it is strictly less than, we will have a dashed line that connects these 2 points. So again, we will choose a test point that is not on the boundary line. Whenever it's possible, I'm going to choose 0, 0, just because that's a very simple value to plug in. So substituting into the original inequality gives us 0 is less than 2, which is also a true statement. So we will shade the region that contains the test point 0, 0. In this example, we have y is less than or equal to 1/4 x minus 3. Let's start with the same first step by changing our inequality to an equal sign. But here, let's use a different graphing technique. You may remember that when y is isolated, that our form is called the slope-intercept form, or y equals mx plus b. So let's use the slope-intercept form and the information found within it to graph this line. We know that -3 corresponds to b, or the y-intercept. So we have our first point, 0, -3. And any time we want to use the slope-intercept form to graph an equation, we start by plotting the y-intercept. So we put a point at 0, -3. Then we use the fact that slope is rise over run to find the second point. So here our slope is 1/4, because 1/4 takes the place of m. Our rise, or our vertical value, is 1. Our run, or our horizontal value, is 4. So starting at the y-intercept, we count 1 unit vertically, 4 units horizontally. We put a second point. And once we have those 2 points, we're ready to draw the boundary line. We look at the original inequality. It contains the or equal to option. So because this symbol is less than or equal to, we will have a solid line that connects these 2 points. Just like before, we choose a test point, and when available, I like to choose the test point 0, 0. So we substitute those coordinates into the original inequality, and we continue to solve. So we're left with 0 is less than or equal to 1/4 times 0 is 0, so that piece cancels. We're left with 0 is less than or equal to -3, and that is a false statement. Because that is a false statement, we want to shade the region that does not contain the test point. So we will shade below the line in this case. For example, so that you can see all the different types of inequalities you may come across in the homework. Here we have x is less than or equal to -2y. The first step doesn't change. We have x equals -2y. We use an xy table to find 2 points that will lie on the boundary line. So we might choose 0 for x and then 1 for y for 2 separate points. So starting with x equals 0, we replace x with 0, and that gives us 0 equals -2y. We would divide both sides by -2 and be left with 0 equals y. So our first point is 0, 0. Second, we would replace y with a positive 1. That gives x equals -2 times 1, or x equals -2. So we have 2 points that we can plot. We plot 0, 0, -2, 1. We look at the original inequality symbol, less than or equal to, so this will be a solid line. Now we want to choose another test point. We can see that 0, 0 is not an option because our boundary line goes through that point. So I might choose one that's close to 0, 0. Let's choose 1, 1. So we take our test point and plug it into the original inequality, giving us 1 is less than or equal to -2 times 1, or 1 is less than or equal to -2. That is a false statement. A positive is never less than or equal to a negative number. So we will shade the region that did not contain that test point. Let's try one more example. Here we have x is less than y. Again, the process never changes, even if the inequality does look different. So first we change the inequality to an equation. I like to use an xy table to find 2 points. I might try 0 and 1 for x coordinates. So first replacing x with 0 gives us 0 equals y. And right away we have the y value. Secondly, let's replace x with 1, and that gives us 1 equals y. And again, right away we have the y value. So we plot these 2 points, 0, 0, 1, 1. We look at the original inequality. It's strictly less than, so we use a dashed line. Now, all the points I would normally use, 0, 0, 1, 1, so on, cannot be used in this case. So we pick a different test point. Let's go up here where we have a point that is clearly not on the line. This would be 0, 2. We take the test point 0, 2 and put it into the original inequality, which will give us 0 is less than 2, a true statement. So because we have a true statement, we do shade the region that contains the test point. And we would be finished graphing this inequality. One more helpful hint before we let you go forward with your homework. When graphing an inequality, make sure the test point is substituted into the original inequality. Do not put the test point into the equation. Otherwise, you might come up with an answer that doesn't make sense.